Hello, welcome to Science Matters. I'm Lawrence Krauss. I'm particularly excited today about the different topics I'm going to talk about for reasons that you'll see. They span the whole breadth of science in exciting ways and really are testimony to the perseverance of scientists and the equipment we can use. Let's start right away with this object right here. It looks like a bit of granola, and it should. It is kind of a cosmic bit of granola. This is an electron micrograph of a little crystal of silicon carbide. Silicon carbide is actually that material. It's incredibly strong and dense, and it's used actually in armor. The police make body armor with silicon carbide. It's so strong. But a crystal like this, however, this is basically just 8 micrometers across, 8 millionths of a meter across. A crystal like this has been a messenger from outer space in a way that's particularly exciting. And I like it because I often think of ways to try and combat the myths that young Earth creationists use about the Earth being 6,000 years old. And they're used to countering the standard arguments about radioactivity on Earth and other things. And every few months, I like to come up with a new one that points out that the Earth is billions of years old and the universe is billions of years old. And this crystal is one way to show it. It's an international group of scientists examined a crystal like this that came from an object that looks like this. This is a meteorite. It's a pretty famous meteorite. It's called the Murchison Meteorite. It was a meteorite that exploded above a cow pasture in Murchison, Australia. And farmers waded through the cow pasture with all the other stuff and tried to find bits of meteorite in between the particulate matter from the cows. And they did. And in fact, you can find many bits of the Murchison meteorite. It looks really quite beautiful. It's a meteorite that shows you that it's an agglomeration of particles that built up, and meteorites are really messengers from not just the outer solar system, but from the beginning of the solar system. This material has not been processed in many cases since the beginning of the solar system, which is over 4.5 billion years old. Mostly they're iron, but there are, as you can see, inclusions of other materials in here. And the farmers actually realized, well, this is an interesting meteorite, so we can actually sell it. And you can find bits of the Murchison meteorite not just as a meteorite, but if you want, you can buy yourself a ring like this or many other things that have bits of the Murchison meteorite. So the farmers were able to exploit this and use it to their own advantage. But many years later, some scientists began to talk to some of the original scientists who'd waded through that cow pasture and got some of this meteorite and began to analyze it. Now, the cow dung that was on the meteorites doesn't matter because what these researchers were able to do was pulverize the material and basically put it in an acid and get rid of everything but the silicon carbide. The silicon carbide material is really a little grain coming from the explosion of stars. When stars are in their final days, they're emitting lots of material, silicon and oxygen, during their processing. And that material combines together to form silicon carbide, among other things. And then organic material combines with it to make a kind of a goop, to make what basically looks like a little bit of granola. And that survives the supernova explosion and goes into outer space and eventually ends up being accumulated in a solar system or a nascent forming solar system like ours, and becomes part of a larger rock like a meteorite. And in fact, in the Murchison meteorite, there are little bits of silicon carbide coming from ancient stars and ancient times. Now, the interesting thing about the silicon carbide is you can date the silicon carbide not by radioactivity, but as that little crystal goes through space, cosmic rays are periodically bombarding the crystal, and we know the rate at which cosmic rays bombard things over time. And every now and then, very, very rarely, a cosmic ray hits one of those silicon atoms dead on and boom, turns it into neon or helium. It breaks it apart. And what these observers were able to do was take that bit of silicon carbide, little bits of it, grains from the Murchison meteorite, and count in a very, very sophisticated mass spectrometer, count the number of atoms of neon and helium, which tells you how long the crystal has been in space. The longer it's been in space, the more atoms of neon and helium you'll find. And since we know the rate at which they're produced, you can determine how long it's been in space. And what they discovered was one of those crystals that looked like the crystal I showed you was 7 billion years old. It had been in space for 7 billion years. That's before the formation of our solar system and halfway back to the beginning of our universe. It's the oldest bit of stardust ever been measured. Older than the Earth, older than the Sun. A lot of the other crystals were about 4.9 to 5 billion years old, and that we think was associated with a big period of starburst formation about 2 billion years earlier in our solar system, in our galaxy, and those stars eventually exploded around 5 billion years ago, producing lots of stuff, including the material, most of the material that makes up our solar system now. But some of those grains were in fact, one that they measured here is the oldest object ever measured, 7 billion years old. It's got nothing to do with radioactivity. It's yet more proof that the Earth is not 6,000 years old. And it's amazing that when we look around at a rock that looks as normal as this, there's something in there that's been around since half the age of the universe and just discovered recently and just analyzed recently. And it's been there under our noses in a cow pasture surrounded by dung for a long time. So that's the first exciting item I wanted to talk about. The next one I want to talk about today has to do with another remarkable kind of measurement that can be made, again, of the cosmos. This picture here demonstrates a recent a paper that just came out by, again, another international collaboration, also, out of Europe, but also out of Australia for reasons you'll see. And this schematic shows this particular system. It's a binary pulsar system. Now, pulsars are neutron stars. Neutron stars are collapsed stars, or what's left over after a star explodes. As I've described before, they're very, very dense objects, billions of tons per cubic centimeter, and you can have a mass of something like 500,000 times the mass of the Earth contained in a region the size of a city. They're very dense objects with incredible magnetic fields, and because of those magnetic fields, when they spin, charged particles get projected out. And as you can see in this image here, from either end of the pulsar, which is a small object rotating that larger object in the center, and those, as the object rotates around, if one of those pulses, radio wave pulses, points towards the Earth, we're going to get a periodic signal. And pulsars were discovered many years ago as being incredibly periodic, beautiful clocks. When they were first discovered, people thought they might be extraterrestrial signals, but we now realize they're the signal of an orbiting, of a rotating neutron star with a radio beacon that's periodically hitting the Earth. But some pulsars come in pairs, and they're wonderful tests of fundamental physics. This particular pulsar pair is 10,000 light years away, and this is a pulsar that is orbiting not another neutron star, but a white dwarf, the dead ember of a giant star that eventually didn't go supernova, it just collapsed and died out like an ember. That white dwarf is still incredibly dense, but it's about 300,000 times the mass of the Earth. And what makes this system particularly special is that the white dwarf formed before the pulsar. So the star had blown off its outer region and just had a very dense core, the white dwarf, and it's spinning. And what happened is this other object, this other pulsar, was once a very large star, and it was orbiting this white dwarf. And as it was orbiting the white dwarf, material would get pulled down to the white dwarf and cause it to spin, because some of the material would come down and give it angular momentum, and it would spin up this white dwarf. Spin it up so this object, 300,000 times the mass of the Earth, is spinning maybe one complete cycle every few hundred seconds, not every 24 hours. And that makes this system unique because the white dwarf, all the material between the pulsar and the white dwarf was gone before the pulsar formed, so it's a very clean system. And this pulsar is orbiting the white dwarf, and when you have a pulsar orbiting a very compact object, it's a beautiful test of general relativity, because there's nothing in the way of that pulsar and white dwarf, and the pulsar is just orbiting around and also rotating. And because there's nothing in the way, the rotation of the pulsar makes it one of the best clocks in nature, as you'll see. And so this system was observed by astronomers using a radio telescope in Australia for 18 years. And they were able to measure something, a prediction of general relativity, that's only been roughly measured on Earth once, because this system has this effect multiplied more strongly by 100 million times. What is known about general relativity is if you have a mass and you bring another mass near it, clocks get changed. They get slowed down in a gravitational field, as I've talked about before. Also, space is clearly distorted. It's curved in the presence of a large mass. But another effect, which was discovered by two physicists named Lenz and Thirring, is that if you have an object that's rotating, a massive, dense object that's rotating very fast, it actually drags space around with it. And what it does is it basically, if you have a system, consider the x, y, and z axes, and if I move it around, they always point in the same directions. But if space is dragged around, then as I move, the x, y, and z axes will be dragged around. And literally, space itself will be dragged because of that rotation. And what happens in this system here is that the white dwarf is rotating in a different plane than the pulsar, and it's causing the whole, because it's dragging space with it, the whole plane of the pulsar's orbit is changing. This is from an image from the paper itself, and it's a little complicated, but basically it's saying that the pulsar, which is rotating itself. That's what's causing the radio signal, and that's in the direction L. And the white dwarf is rotating in the direction S, and the two are precessing because of an interaction with each other. And that precessing, that bending of space, is due to two different things. One is a classical effect that because the white dwarf is spinning very fast, it's not exactly a perfect sphere, and it's bulged at the ends basically, and in the middle, and that causes an effect that also causes these two orbital planes to rotate a little bit. But the key effect is the Lenz-Thirring effect. In the Earth, it's been measured, but it's so difficult to measure, we had to send up a very sophisticated satellite called Gravity Probe B, and it measured a change in a clock and basically a twist in the way this gyroscope was pointing by a very, very, very small effect. It was just barely measurable after many years and a lot of money. But because the white dwarf is 300,000 times the mass of the Earth, and the pulsar is 400,000 times the mass of the Earth, and they're very close, this effect should be 100 million times bigger in this system. And these observers knew that and measured the system for 18 years. And this is kind of a video that actually came from Swinburne University, from one of the observers. And what you can see is the pulsar is moving around the white dwarf. And of course, its jets are moving around as it's orbiting around, as it's rotating. But watch the plane, the whole plane of that orbit is gonna bend a little bit. And that bending is due to the white dwarf taking space and curving it around with it. Because as the white dwarf is rotating, the reference frame, the x, y, and z axes themselves of space are themselves bending. Matter not only bends space by its presence, but if it rotates, it drags space along with it. And in a moment, you'll be able to see sort of a schematic of the reference frames of this whole system changing. And there you can see as the white dwarf is spinning around, it's dragging, what's called frame dragging. It's actually dragging space with it and causing the orbit to precess. It's not a huge effect. It's incredibly small, but it's still 100 million times bigger than that on Earth. And what I want to show you, which is what makes this amazing, is that this was taken over 18 years. I want to show you some data, and obviously you can't read all of this, but what's amazing about this system is it's so clean that you can measure numbers to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 significant digits. Measure the period, the frequency, everything, its mass, everything to incredibly high precision because it's so clean. And the effect that we're looking for is as the orbit changes in its direction towards the Earth, the time it takes for that signal to come to Earth changes a little bit. And this is the amazing thing. There's one number there that's called the first derivative of the pulse frequency. And what it is, a number that basically tells you how, the first derivative of x is a number there. And what that is tells you how much the clock is changing. If you make one tick each time the pulsar goes around, what the rate of change of that clock is, how good a clock is it. And it's a number times 10 to the minus 13 seconds per second. And what that means is every second the clock is accurate to 1 part in 10 to the 13th. And that means that in 1,000,000 years, this system will change by 1 second. It's got an accuracy almost better than an atomic clock. But because we can measure it so accurately, the very small effect of gravity of causing that tilt of 1 part in 10 to the 13th, 1 second every 1,000,000 years can be measured. And this system has now been measured. And for the first time, it's been shown that this effect of fame dragging is the dominant effect probably in this system, and it's been measured cleanly and unambiguously. And I just find it so beautiful that there are objects out in the universe that are incredibly dense, incredibly violent, but incredibly peaceful at the same time, and such a beautiful, clean system that allows us to test the laws of physics to 1 part in 10 to the 13th. The lens tearing effect, the dragging of space, has now been measured by this system, and astronomers who were patient enough to observe it for 18 years continuously and measure things to this kind of accuracy. Now, I want to come back to Earth for the last 2 bits of this segment, and the first one involves an international collaboration. That this is a picture. What's it of? It's not of a star. It's basically a picture of the oceans of the Earth and the heat being emitted from the oceans of the Earth. And this international collaboration analyzed data from the 1950s through 2019, and an international team of scientists determined that the average temperature of the world's oceans in 2019 was 0.075 degrees Celsius, or 0.135 degrees Fahrenheit, higher than the average between 1981 and 2010. So in 2019, it was hotter by about 1/10 of a degree Fahrenheit than it was for the years between 1981 and 2010. Now, a lot of people say, big deal, 1/10 of a degree. And the point is, it is in absolute value a small number, but remember I told you in the last episode that the heating of the oceans is taking place over time and is going to continue for hundreds of years and cause the oceans to expand and affect the climate in the Earth. But what these people did was try to give a different sense of how big an effect this is rather than a small effect. So if you take the amount by which the oceans have increased, remember there's a lot of water in the oceans. It takes a lot of energy to heat up that much water by 1/10 of a degree. And they found various different ways to express it, which I thought were interesting. The amount of heat we've put in the world's oceans in the past 25 years is equal to 3.6 billion Hiroshima atom bomb explosions. As if we'd set off 3.6 billion Hiroshima-scale atom bomb explosions in the ocean. Had we done that, we would have heated up the ocean by that amount. Maybe that doesn't impress you. There's another different way they've explained it. It's about 5 Hiroshima bombs of heat every second, every day and night, 365 days a year for 25 years. It's like, another way of saying it, it's like every person among the 7 billion people on Earth constantly pointing 100-watt hair dryers at the ocean every second of every day. We are dumping a tremendous amount of heat. When you look at a number like 1/10 of a degree, it may seem very small, but it's only small if you present it that way. If you think about how massive the ocean is, we have been dumping heat into the Earth because of the greenhouse effect at a huge level. And one of the authors at the end of the paper, discussing the paper, said if none of these numbers impresses you, perhaps there's a better colloquial way of describing how much heat we've been dumping in the Earth. And I quote him, he said, the less technical term is, it's a shit ton of energy. And so we've been dropping a shit ton of energy into the ocean in any of these forms over the last 25 years, and that is the level at which we're changing the climate. Well, talking about heat, of course, one of the hottest objects near us is an object we all recognize, which is the sun. The sun generates the heat that keeps us going. In fact, there's 10,000 times more energy hitting the Earth's surface every day from the sun than humanity uses. But I've talked about this once before. As hot as the sun is, and as much energy as it is emitting through all the effectively hydrogen bomb explosions that are happening inside the sun every second, billions and billions of them, most of the energy of the sun isn't emitted in heat. It's actually emitted in a form of my favorite particle in nature, neutrinos. The nuclear reactions in the core of the sun emit energy, but they also emit neutrinos. And neutrinos are elementary particles that are so ephemeral, they interact so weakly with matter, that they escape the sun essentially instantaneously. And we are bombarded now by neutrinos from the sun. Every second of every day, about 600 billion neutrinos are going through every square centimeter of my and your body every second, coming from the sun. And the problem is, most of those neutrinos, almost all of them, go right through the Earth without ever even knowing it was there. The average neutrino from the sun will travel through 10,000 light years of lead without having a single interaction. How do we detect such neutrinos? With big underground detectors. They're so big that though most of the neutrinos are going right through, of the billions and billions and billions of them that are interacting every second, maybe 1 or 2 a year will interact, and the experimentalists look for that. And so we've been able to detect solar neutrinos, and several Nobel Prizes have gone from the discovery and observation of solar neutrinos. Now, there's another object much closer to us, much cooler to us, that isn't having hydrogen bombs going off in its core every second, and it's an object that's more familiar, or at least equally familiar. It's the Earth. The Earth is not having nuclear reactions heating it. It's not a star, so it's not powered by nuclear reactors in that sense, or by fusion reactions. And it looks fairly passive. But the Earth is emitting heat. The Earth is still hot. It's got a molten core. And we know that the Earth is emitting into space about 40 some odd terawatts of energy every day. Now, 40 terawatts of power, I should say, of the power the Earth is emitting into. That's the rate of energy emission by the Earth. That's coincidentally about 4 times the amount of power that all of human civilization uses. We use 10 or 20 terawatts in all of the processes we use every day. But the Earth is cooling. It's emitting that much, 40 terawatts of energy. Now, I want to hasten to add that when I say the Earth is cooling, people who are global climate change deniers shouldn't say, "Oh, it's great that we're adding heat like we are to the oceans." The Earth itself is cooling over billions of years, and that is generating heat into space. But the climate is determined by the energy being received from the sun and the amount that goes out from the sun. I remind you that 10,000 times as much energy is impacting on the surface of the Earth as we use. Most of it's radiating out. And the fact that we are producing greenhouse gases that are trapping that is affecting the climate. So the global cooling of the Earth due to the fact that it was once hotter, sure, in a billion years it'll be a little cooler, but that's not affecting things on human scales. So it's not as if we want to input energy like we are into the oceans to combat the cooling from the Earth. They're two totally separate things, and you shouldn't confuse them, and it shouldn't be used as yet another argument to do nothing in the face of human-induced global climate change. But in fact, it's not all coming from cooling, because there are radioactive materials inside the Earth. Not a lot of them, but trace elements of radioactivity: uranium, thorium, potassium. And it's been a question for a long time how much radioactivity is in the Earth, and how much of the heat emitted by the Earth is coming from radioactivity in the Earth instead of cooling. There were good ideas about how much there might have been. And about 35 years ago, I first began to learn about this. And I was amazed that we really didn't know how much radioactivity there was in the Earth. I was also amazed to find that most of the radioactivity was thought to be near the surface of the Earth. Because after all, radioactive elements like uranium and thorium are heavy. Why shouldn't they have sunk to the core of the Earth? And the answer is they're actually large molecules, and when the Earth was molten, they kind of floated up near the top. I began to learn this because I realized, well, the radioactive decays produce neutrinos. Actually, they produce particles called antineutrinos. And I realized that the Earth is a source of antineutrinos, just like the sun is a source of neutrinos. And I did a calculation, and the point is the Earth, of course, is not emitting anywhere near as many antineutrinos as the sun, which is this dense fusion reactor, is emitting, but the Earth is much closer. You can work out that there's about 10 to the 25 antineutrinos emitted every second by the Earth. Another way of putting it is, in every square centimeter of your body, now coming up from down below, 1 million antineutrinos are going through your body, emitted by the radioactive decays inside the Earth. That's about 10,000 times less than the number of neutrinos coming from the sun. But I began to wonder if we might ever be able to measure it. And I spent a long time and worked with several colleagues and wrote a paper saying this would be really hard, but if we could do it, we might learn a lot about the interior of the Earth. But I never imagined it would be measured in my lifetime because it was so hard. But, of course, I'm not an experimentalist. And 35 years later, what looks like a massive disco ball, here is this, it's part of an experiment called the Boricsino Experiment. It's a large liquid scintillator experiment. This is a rotten image of it, but it's a huge several-ton ball of an object called liquid scintillator. It's organic materials inside photomultiplier tubes inside of a tunnel in a mountain in Italy. And that mountain shields all the cosmic rays except for the neutrinos. And this was designed, it's called the Boricsino detector, because it was looking for a certain type of neutrino from the sun. It was designed to look at neutrinos from the sun. But what's amazing is it was realized that it could look at the antineutrinos coming from the Earth. And after about 10 years of study, this brought me, when I first saw this from this paper that just came out, it really brought back memories, because this is very similar to a figure I produced 35 years ago predicting what they might see. This is them also imagining what they might see. And they realized they could measure antineutrinos coming from the Earth, because an antineutrino would bounce into a proton, turn it into a neutron. It would also emit a positron in the process. That positron would annihilate with an electron, producing two gamma rays, which they could measure, but then the neutron would wander through their detector and eventually combine with a proton, forming deuterium, emitting another photon that they could see, and that was a unique signature of an antineutrino. And after 10 years of study, what they've discovered was that they have measured 53 events that are antineutrinos coming from the Earth. It's an amazing measurement that, again, I never thought would be able to be done. And what have we been able to learn about it? Well, remember that the picture of the Earth has an inner core which is solid, an outer core which is liquid, and then the mantle which is convecting heat up. And the question is, where is the heat coming from? And by building this detector, and basically in this area of Italy, they were able to measure these neutrinos and discover that more or less of the 47 terawatts of energy, of power coming out of the Earth, about 38 terawatts is coming from radioactivity inside the Earth. Only about 10 is coming from the Earth's cooling. And they were able to verify another thing that was only speculated, that most of the radioactivity is near the surface. And another question that had been an open question, is there a nuclear reactor going on inside the core of the Earth? And they're able to show that it isn't. The only way we can probe the deep Earth in this way is by looking at particles that come out from inside the Earth. And antineutrinos have now given us a new handle that tells us about the structure of the Earth, something that I speculated about with some colleagues 35 years ago, figured never would be possible, and now that these detectors have been built and able to do it. So once again, you should never say never. And you should never underestimate the imagination and perseverance of experimentalists and the ability of science to measure things that we might otherwise think are impossible. Science matters.